pointer on pointers, or give you a reference for references, is Trey Hunner. Please make him welcome.
So, very brief introduction before I get started. My name is Trey, and I help folks level up their Python skills. I do that through Python Morsels, which involves deepening your skills by solving interesting and practical Python exercises. And I also hold team trainings on both introductory and advanced Python topics, as well as technologies like PyTest and Django. If you would like my help leveling up your or your team's Python skills, contact me. One of these faces is white, and one of them is black. One has a dark background, and one has a light background. At least it looks that way. These faces are actually the same color. These faces are both a shade of gray that's right in between white and black. This optical illusion happens because our brain is trying to correct for what it perceives as a difference in the quality of light around these two faces. Our brain is constantly modeling the world. Our brain's mental models help us understand the world around us, and they're usually pretty great at doing so. But every model has its flaws, though even incorrect models can still be useful. Let's test your mental model of Python's variables. If we assign a variable first to an empty list, and then we assign a variable second to first, and after that we append 9 to second, second now has one element within it. The question that we're going to consider, which I don't want you to say out loud right now, is how many items are in first? So let's compare a few different mental models to see how each one might answer this question. First, let's try to mentally model variables as buckets that contain objects. If we assign a variable to an empty list, that variable contains that list. Then when we assign another variable to the first one, the list is copied into a new bucket. Let's say we then append 9 to the second list, which would mutate the second list. But the first list shouldn't change, except in Python, it does change. This mental model doesn't work, at least not in Python. Variables in Python are not like buckets that contain objects, and assignment statements don't copy anything. So let's try another mental model. Let's mentally model variables as sticky notes on objects. When we assign a variable to an empty list, we attach that variable name to the object. Then when we assign another variable to the first one, we simply attach another name to the same object. So when we change the second list, the second one changes. But the first one also changes, because there is no first list and second list. It's all just one list. This is the mental model that you'll see used in many books on Python and in many introductory Python courses, and it works pretty well. But as we'll see later, it does have its limits. So let's try a third mental model. In this third model, we'll think of variables as living in variable land, and objects as living in object land. When we assign a variable, we draw an arrow from the variable to the object. When we assign another variable to the first one, we draw another arrow from the second variable to the same object. So if we modify the second list changes, and so does the first, because they're the same list. I call this mental model pointers because it looks like variables point to objects. Now, if you are thinking, you're looking at that word pointer and thinking, that word has a specific meaning, and Python's variables are not pointers. They're object references. Well, actually, according to the Python documentation, they're bindings. But I'm going to call them pointers with the caveat that they're not like pointers in C. You can't dereference them. There's no pointer arithmetic. So I will not be using the term binding. I find it kind of confusing. Though I will sometimes use the term reference, but I'll mostly say pointer because that's a very visual idea that all of us are familiar with. Before we talk about the word pointer, let's talk about the word change. In Python, this word can be a problem. Sometimes Python learners will tell me, I've assigned two variables first and second to the same object, and when I change first, second doesn't always change. When I change first this way, second changes. But when I change first this way, second doesn't change. Why? The word change is the problem here. There are two different types of change in Python. Assignments change variables, and mutations change objects. Let's use our pointers mental model to help us differentiate these two types of change. When we append to first, we're mutating the object that first points to. Since second points to the same object, accessing second will show the same changed object. But if we reassign first, that changes which object the variable first points to. But that doesn't change the second variable at all. Second still points to the same object as before. So variables in Python do not contain objects. They point to them. Because of this indirection between variables and objects, there are two distinct types of change. This is why the word change can be ambiguous. Mutations change objects, and assignments change which object a variable points to. So in Python, we have two different types of change, but we also have two different ways to ask the question, are they the same? We have the double equals operator for equality, and we have the is operator for identity. You can think of equality and identity as asking about model numbers and serial numbers. If I'm in the market to buy a washing machine, I might ask, what's the model number? Because I'm hoping to look up reviews for what should be equivalent devices. But if I need to call customer support to report an issue, I might give them the serial number. The serial number uniquely identifies the machine. Equality checks are like a comparison of model numbers. They ask whether two objects represent the same thing. Identity checks are like a comparison of serial numbers. They ask whether two objects are identical, meaning they aren't even two objects, they're exactly the same object. Though really, identity isn't actually even about objects. It's actually a way to ask whether two names point to the same place. If we have two variables first and second, and we ask whether they're equal, we're asking whether they have the same value. This asks the objects whether they represent the same thing. If we ask these variables if they're identical, we're asking whether they both point to the same object. Unlike equality, identity doesn't actually ask anything of the object itself. So equality compares the values of objects, while identity compares references to those objects to see whether they are the same reference. The is operator is very rarely used outside of comparisons to none. When we ask, are they the same, we usually want the double equals operator. Checking equality is much more common in Python than checking identity. We have been talking mostly about variables and how they work. We haven't really discussed how objects work. Let's start inspecting Python's objects by playing with data structures. Let's make a 3-item list called row. We'll then make another list called boat that contains row, row, and row. So the boat list contains 3 lists, which each contain 0 3 times. If we assign to index 1 within index 1 in the boat list, what changes? Index 1 in boat is the middle item, which is a list. And index 1 in that sublist is its middle item. So we're changing the middle item in the middle list. Sort of. It looks like we changed a bit more than that. Every sublist within boat changed. In fact, even row changed. I've been using the word change here, which, as we discussed, can be a tricky word. But I also used the word contains. The word contains can also cause confusion. Data structures in Python don't actually contain objects. Data structures can only point to objects. Let's take a look at what's going on here by revisiting two of our mental models from before on sticky notes and pointers. First, we'll take a look at our sticky note mental model and ask what should happen if we put our second list inside another list. Should we add another sticky note that says which list it's in and which object it's at? And also, what if we point another variable to that new outer list? Would we need to add yet another sticky note with another name and another index? This does work, but it seems kind of complicated. This sticky note mental model works well for explaining how variables in Python work, but it doesn't work very well for explaining how objects work. So, if we look at our pointers mental model, we'll see that, starting from the beginning, when we assigned the first variable to an empty list, we drew an arrow from the variable to the object. Then when we assigned another variable to the first one, we drew another arrow from the second variable to the same object. So when we modified that second list, the second list changed, and so did the first, because they're the same list. But before, our diagram didn't quite look like this. This time our list has an arrow pointing to an integer. Why? Well, variables don't contain objects, but objects also don't contain objects. Objects can only point to objects. So index 0 in this list points to the integer 9. That's also why, if we put our list inside another list, we'll be pointing one of the indexes in that new list to our existing list. Variables can point to objects, and objects can point to other objects. But nothing ever points to variables. Variables are just a name that refers to an object. This pointers mental model is a bit more complex than the sticky note model, but it stretches a bit further. The indirection between variables and objects is tricky, but it also makes it easier to understand how data structures actually work in Python. In Python, containment is a slightly misleading term. Data structures don't actually contain data. Data structures contain references to data. But this isn't just about data structures. This is about pretty much every object in Python. So let's say we make our own objects using a class like this. This class accepts a list, and it stores that list as an attribute on our class instances. Calling the add task method on an instance of this to-do list class will add a new task to the end of the tasks attribute for that class instance. If we pass the same list into this, we'll end up with two instances that have the same attribute. But what if we mutate the tasks list on one of those two objects? Will it affect the other one? It will. Attributes, like variables, don't contain objects. They point to objects. This might seem like a really big issue, but this problem has a pretty common solution. In this class, we could use the list constructor to copy the passed-in list. Now, when we make two instances of our class by passing in the same list twice, modifying the tasks list on one of these instances will not affect the tasks list on the other. Also, as an added bonus, this class now accepts not just lists, but sets, generators, or any iterable, because the list constructor will loop over any iterable that we give to it and make a new list that contains all of the items from that iterable. So for many classes that are meant to change the data that's passed into them, that data is often copied when a new instance is initialized. Variables don't contain objects. They only contain pointers to objects. But objects also don't contain objects. Whether we're talking about indexes or attributes, objects only contain pointers to objects. So when we say we've made a list of lists, this is a shorthand. We actually mean that we've made a list where each item acts as a pointer to another list. And in fact, when we ask whether our list contains a specific object using Python's in operator, we're asking whether our list contains a reference to an equivalent object. So assignment changes which object a variable points to. And this is what an assignment looks like in Python. But this isn't the only way an assignment might look. Import statements also perform an assignment. And so does each iteration of a for loop. And so do function definitions and even class definitions. Anything that updates what a name points to performs some sort of assignment. But what about plus equals and minus equals? These are often called augmented assignments. But do they perform an assignment or a mutation? Well, it depends. Let's say we have two variables, a and b, that both point to the same list. If we use the plus equals operator to add more elements to b, what happens to a? Did a change, or is it still the same? When we look at the variable a, we'll see that it did change. Augmented assignments actually perform a mutation. So using plus equals on a list doesn't make a new list. It mutates the existing list. That's why plus equals is often called an in-place addition. In-place operators are designed to mutate. But wait, doesn't plus equals work on strings? Strings are immutable, which means you can't change a string object. But strings do work with plus equals. If plus equals is an in-place addition, how does it work on strings? Well, augmented assignments can perform a mutation, but they don't have to. It's up to the objects that they're working with. If an object doesn't specially handle plus equals, then Python falls back to a plus operator and a plain old assignment. The distinction between assignments and mutations isn't always clear. Augmented assignments do perform an assignment, but they also mutate, or at least they can. But this assignment mutation fuzziness isn't just about augmented assignments. It comes up in other ways too. Assigning to an attribute is an assignment, but it mutates the object that the attribute lives on. And assigning to an index in a list mutates the list. These are assignment statements, but they also mutate an object. Modifying where an attribute or an index points to must mutate the object that the attribute or the index lives on. And if you squint hard enough, every assignment is actually also a mutation of some sort of namespace. It may not be a namespace that we can access directly through a variable, but all variables live somewhere. Assignments change which object a pointer is pointing to, but objects can contain references to other objects. And when our assignment target is an index, a key, or an attribute, that pointer lives within an object. So when we use an assignment statement to change where an attribute is pointing, that mutates the containing object. Speaking of mutating objects, let's talk about tuples. Once you've made a tuple, you can't change it. Or can you? You cannot mutate a tuple, but you can change the value of a tuple. If we put a list inside a tuple, what would happen if we tried to change that list by appending a new item to it? Python allows this. If you can get a reference to a mutable object, you can mutate it. But this also seems to change our tuple, and yet tuples are supposed to be immutable. Are they? If we make two equal tuples and we mutate an object that one of those tuples contains, that will change the value of the tuple, meaning the tuples aren't equal anymore. Tuples are immutable, but an immutable object that can store a reference to a mutable object can potentially have its value change. In other words, immutability is a shallow concept. We can't directly change a tuple, but we can change objects that tuples refer to. And since the objects that a tuple contains affect the value of the tuple, that changes the tuple. in some sense of the word change. So that means that tuples that contain mutable objects can have their values change. In Python, variables don't contain objects. They only point to objects. Put another way, variables store references to objects. And objects can store references to other objects. But objects can't contain objects, and immutable objects that contain references to mutable objects are only kind of immutable. So given what we've learned about how variables and objects work in Python, if we take an empty list called x, and we call x.append x, what would x be? This won't end up being a list that contains an empty list. Instead, we'll get something that looks like a list that contains itself, because that's possible in Python. A list can contain itself, sort of. As we know, data structures don't contain objects. They contain references to objects. So this list contains a reference to itself. We have just made an infinitely recursive data structure. This is possible because objects in Python don't contain other objects. Both variables and objects can only contain references to objects. So there's nothing stopping a list from containing a reference back to itself. There are many odd corners of this topic that I did not cover. For example, we didn't just discuss variables and scope within Python, hashability, optimizations around numbers, strings, and tuples, of which CPython has many, arrays and direct value storage that pandas, NumPy, and other libraries rely on, mutable default arguments, and various reference-based gotchas. This URL, which is on the bottom of each slide in this talk, includes links to resources on some of those topics, as well as 2 really great talks by other Python community members on this topic as well. Before we wrap up, I do want to address a common question. Why does Python work this way? Wouldn't it be easier if variables and data structures contained objects and assignments copied the objects when we were assigning? Well, imagine if every assignment made a copy of an object. Copying objects all the time takes time and it takes memory. But also, how would we ever model parent-child relationships or any kind of relationship that involved storing a reference to an object instead of a copy of an object? Would we need to make some kind of distinction between assignments that copied and assignments that made a reference? Other programming languages have done that before, and it requires adding another layer of complexity to the language. Python's way isn't necessarily the right way, but most days I really appreciate the trade-offs that Python made around this topic. Python's separation between variables and objects can definitely be confusing, but it's a pretty decent approach to a hard problem. Every decision in life has trade-offs, and everything is relative to its possible alternatives. Whether we're talking about a software feature or about politics, when we say this thing is bad, we should always ask ourselves, compared to what? We should acknowledge problems with the status quo, but we do need to be honest and think deeply about real-world outcomes. Thank you.